Good day. In our last class, we discussed derivative of function. We have defined derivative of function in two ways. The first one is that if you have derivative of a function at a particular point, and second one is derivative of function at any point. Okay, so you recall that we give this definition of derivative when at any point of x as the limit of f of x plus h minus f of x all over h. Okay, so we have defined this function, derivative of function at any point. So if this x is a particular point A, okay, so we have wherever we have x here, we put A. Okay, so this means a derivative of function at a particular point of A. So we have also given several examples of a derivative of function at any point. Okay, so today we add one more example before we move to another fantastic definition of finding the slope of a function. So today again, we want to add to the previous example, this example, find the derivative of f of x equal to the square root of x. Okay, when we find derivative of a function, this. Okay, so and also, what should be the domain of the derivative? What is the domain? What is the domain of f prime of x? Okay, so also want to know. The reason why I want to know this is that the domain of this function ranges from 0 to infinity. So we want to see the domain in relationship relative to its derivative. Okay, so let's first of all find the derivative before we talk about the domain of the derivative. Solution. So here we are given f of x equal to the square root of x. Okay, so one of the terms we have in the formula is this, and this implies whenever we see x, we should put x plus h. Okay, so therefore the derivative for a function, as we have it earlier, we make use of the formula this. So we substitute the term here minus this term. So this will be the square root of x plus h minus the square root of x all over h. Okay, so if we evaluate this at h, okay, if you do the direct substitution here, you will observe that putting h to be 0 here, okay, this gives 0 over 0, okay, which is indeterminate. Okay, in order to avoid that, we first of all rationalize this term before we evaluate. Okay, so how do we rationalize? Okay, we take the term this term x plus h minus the square root of x, okay, multiply it with the term when the sign is changed to positive, and that will be x plus h plus the square root of x, everything divided by h, which is this, then multiplied by the square root of x plus h plus the square root of x. Okay, so we further simplify this. So you will see that the term here, okay, is like this term, which implies difference of two squares. Okay, so anytime you have a term like this, Under the elementary expansion, this implies a squared minus b squared. Okay, so we'll use this for the what we have in the numerator here. So we are transferring this to this place. So this will be the limit as h tends to 0. Okay, when we expand this using this uh, equation above, so this becomes the square root of x plus h square minus the square root of x all square. So everything here over h into the square root of x plus h plus the square root of x. Okay, so we are only using this to expand what we have as the numerator. So this becomes the limit as h tends to 0. So this becomes x plus h, because this square will cancel the square root, and this is minus x. Okay, this will also cancel the square root. So everything here is over h into the square root of x plus h plus the square root of x. And this is equal to the limit as h tends to 0. Okay, here this is positive and negative x. Okay, so they remove one another, and this becomes h into h square root h over h into the square root of x plus h, and this. Okay, so again, this h cancels h, so this reduces to the limit when h tends to 0, 1 over uh, the square root of x plus h plus the square root of x, and this is equal to the limit. Okay, when we apply the limit, or when we apply the limit to this, so this becomes 1 over the square root of x, because this becomes 0. So x plus 0 is x plus the square root of x. So everything is 1 over 2 of this square root of x. Okay, so this is the derivative of the function f of x equal to the square root of x. Okay, now let's see the domain of this function. Okay, and compare to the original function. So you will recall that we are given a function f of x to be the square root of x, y, according to what we solve, we have this function f prime of x is 1 over 2 square root of x. Okay, so the domain of this function, okay, as I said, is range started from 0 to infinity. It is 0 because any term on the square root must be non-negative. Okay, so the domain here is from 0 to infinity. Okay, 0 inclusive, but here you will see that when we can't put 0 here because it's beyond defined, and because of that, 0 cannot be part of this domain of this function. So when we remove 0 from the domain, okay, any time after 0 will be the domain of this function. So this becomes this. Okay, so you will now see that the domain of the slope of this function is smaller. This domain is smaller than this. Okay, so anytime we are finding the derivative of function, okay, so we need to check, okay, what is the domain of the original function and what is the domain of the slope of that function. Okay, so this will be able to tell us the interval at which a function like this is differentiable. Okay, and that is where we are going now. Okay, so this is telling us something. It's telling us that this function can be continuous from this point 0 to infinity, but it's continuous at 0. But here, this function is not differentiable at 0. Okay, so let's now give an intuitive definition of what the differentiability of function is. Okay, so we title this differentiation. Differentiation. Okay, so let's have a definition of this. A function f of x is said to be differentiable. Is said to be differentiable at the point x equal to a if its derivative, that is the derivative we defined earlier, if it exists. If it exists, okay, so that is when we say if a function is differentiable. If the derivative exists at at a particular point, okay, we say it is differentiable. So another way of looking at differentiability, okay, we can have an alternative definition which goes thus: that a function f of x is said is differentiable at a particular interval. Okay, a function f of x is differentiable at a particular point at a particular interval if it is differentiable at every point of the interval. Okay, so this is what differentiability of function means. Okay, we cannot give a definition. We can start from the last definition we just last example we just concluded, where we have a function of x to be the square root of x. So, okay, so let's look at the differentiability of that function. Okay, so this is taken. So let us remove this. So since we have the derivative of this function earlier, so one can pose this question. So is f of x equal to square root of x differentiable at x equal to 0? Okay, so here is a question we need to ask. Okay, so we'll now see whether to check this, we'll see whether the derivative of this function exists at 0. Okay, so earlier we know that the derivative of this function is given by this. Okay, so as we earlier see, this is the derivative of this function. So at x equal to 0, let's see what happens. At x equal to 0, f prime of 0 will be equal to 1 over 2 into square root of 0. Okay, and this 1 over 0, which is undefined. Okay, which is undefined. So because of this, okay, the answer to this will be no. The answer to this will be no. I will say this is because at x equal to 0, f prime of 0 is undefined. Okay, so this function is not differentiable at 0. But any point after 0, okay, we can say the differentiability of this function was. Let's see another example. Another example. Okay, so let's give this in general case. the functions sin x, cos x, and exponential x, okay, are differentiable, are differentiable at every point, okay, or let's say everywhere. The functions sin x, cos x, and exponential x are differentiable everywhere in the domain R. Okay, so it means when we find the derivative of this function, okay, earlier in our previous video we have that derivative of sin x is cos x. Okay, so when we look at cos x, okay, is there any point at which cos x will be undefined in the domain R? Okay, is no. Okay, so because of that, so this function is differentiable everywhere in R. Same thing for cos x, whose derivative is negative sin x. Okay, and same thing for exponential s, whose derivative is also exponential s. Okay, so these three functions are differentiable everywhere. Okay, so example of functions that are differentiable everywhere are all polynomial functions. Okay, so let's say this is example 2 and let's have 3. Okay, all polynomial functions. Okay, all polynomial functions are differentiable everywhere in the domain R. Okay, so one can think of any polynomial function depending on the choice of the degree. Okay, so all of them are differentiable everywhere. Okay, so let's now look at some specific case where functions continuous everywhere except as a point. Okay, so let's say example 4 now. So the function f of x equal to ln x is differentiable everywhere except at x equal to 0. Okay, so let's see why we make this conclusion. Okay, earlier we have shown that the derivative of, in our earlier video, we have shown that the derivative of ln x is 1 over x. Okay, so this function, when we observe it, you will see that if you pick any point from this line, negative infinity to positive infinity, okay, so this will be defined. If you pick any point within the uh, domain, okay, this will be defined. And when we get to 0, okay, when we get to 0, this will be f of 0 equal to 1 over 0, which is also undefined. Okay, so any point aside 0, this will be defined. Okay, so that's why we make the conclusion that this function is differentiable everywhere except at x equal to 0. Okay, so one can see this as 0. Okay, so we have this case which is undefined. Okay, so other examples are example. Okay, let's give a case of another function. Function. Okay, a rational function this time. The function f of x equal to 1 over x plus 1. Okay, is also differentiable